is part of theories that you want to do AI for math, but given I'm in a unique position, I'm a computer scientist, and I happen to have a joint appointment in the math department that has to be renewed every 3 years. So instead of doing AI for science or math, I will do math for AI, and machine learning, so that it will help my next appointment here. But clearly these are all intertwined, and in modern days, there's almost no boundary between the domain. So I will have a relatively simple talk, and talking about a very simple concept called regularization, and their roles in understand learnability. So okay, so it is working. So the main body of the talk is joint work with two of my colleagues at CS, Sharding and Vato, and two brilliant students, Julian and Sid. And I will end with some of the extension of the discussion, and some are joint work with my math colleagues, Xiaohui, and our common student Zhixiang, and our current first year student too. So they are all here. So like every problem, they have some random reasons why somehow we began to think about them, right? Particularly as a mathematician or theoreticians, that when we somehow come across a problem, if they draw our attention long enough, ultimately the curiosity took over and we began to study them. And then we somehow lose track of why we study them. And so here, particularly, we actually had a memory of how actually we started working on this. So it's like a long journey, started with a single word. And so I keep on pressing in the other direction. So about 14 years ago, CS hired a brilliant young star. So you have to think about this 15 years ago. And his name is Xiaoding Dogmi, and he came from Stanford, rising star in convex optimization and computational game theory. Okay, so as we know, California is very nice. We really sit indoors, so we go outdoor, right, to show our beautiful campus, which I did when he first came, and then we walk around the U.S. As we walk around USC, this conversation will never happen today, right? It's only 15 years ago. You just show you how far it come. And I just asked him an innocent question: do you understand machine learning? And it turned out Xiaoding is very straightforward. And so he gave a one-word answer, essentially. Not even a little bit, right? So usually it's hard to carry a conversation like this. Xiaoding is very talkative, but so, but his frankness also drew my frankness. So I started with, I actually know nothing about it either, right? So because I mostly study graph theory, geometry, and a little bit of game theory. And so I see many problems through the lens of, graph, geometry, and so on. And so Xiaoding began to say something deep. This really showed why he's rising star and brilliant scholar. And he basically said, I don't understand any of the words in machine learning. Right? That's what they said, right? So this is a wonderful sentence to have a conversation, right? Because the best way to answer is which word? Give me an example. And he gave me an example called regularization. Right? So this clearly shocked me because he is an expert in convex optimization, and regularization showed up all the time, right? So this also shows why he's a deep thinker. He's not talking about he doesn't know the notion of regularization. He basically said, I don't understand the mathematical connection between why regularization can directly connect with learnability. So it's a much deeper question, right? So while we have coffee, clearly neither of us understand regularization in machine learning. And as a theoretician, I think one of the simple ways to do research, particularly about something you know nothing, It's just pretend you know something and make conjectures, right? Making conjecture is the most important thing for mathematics. So while drinking coffee, we began to think about conjectures. And so what is regularization? We all know in machine learning, it's trying to use to overcome the overfitting, right? Machine learning largely in today's statistical machine learning is basically try to reduce learning to optimization, right? To choose a model that somehow come closer to observation, and hoping this model will be good for future, right? So that's at the highest level. And so come really close to observation, that's usually we call the empirical risk minimization. We want to come closer to empirical observation. And this one can also show both in theory and in practice, can introduce overfit and hence lose the capacity of learning, right? Overfitting is not just for students, right? You know, usually our students overfit for exams, right? Exam high doesn't mean you learn better, right? So this is a similar things that you have a particular objective for exam, you may score high, that means you get the best model.
The AI overfit for the benchmarks, right?
So essentially, then people try to make learning more robust, just like in practice, we make student learning more robust, right? So this is essentially broadly the concept of regularization.
What does overfitting mean?
Overfitting basically is you have a particular objective function, like a loss function. You just want to score as high against that loss function, right? So you overfit to the exam, to the objective function. But learning is much complex and broad phenomenon. Right? It's not like one or two simple objective function can fully characterize. So that's why you might overfit towards the direction of an innocent objective loss function. Right? So, you know, just like bounded rationality, right? Every loss function has bounded rationality, right? So it's only bounded to that aspect, right? So, but regularization is tied with a beautiful principle of learning, which a principle almost all mathematicians appreciate. That's called Occam reason, right? That is to say the simplest way to explain are the best way, right? We all appreciate simple proofs rather than very complex proof. The simple proof are the best proof, right? So this principle, I think, in some sense, are deep in machine learning, and so broadly schema-wise is that usually when we directly reduce to optimization, we try to minimize training errors, namely come close to the observation. And in the Occam reserve philosophical framework, sometimes we call structure risk minimization, we consider a regularized term in some sense to counter the robustness of the training errors optimization, right? So this is a one-step framework over just to come closer to the observation, right? And so a lot of regularization came in this form, but they can come in different form. And this will be the form which I will mostly focus on today. So as I mentioned, as a theoretician, to think about problem you know nothing about, the best way is to make conjectures. And while we sit in the coffee, we began to make our conjectures to see how do we guide our discussion if next time we meet, right? So we began to eventually convert into this conjecture. That is, can we prove under certain framework of learning that anything is learnable by regularization? That it will show regularization is a kind of universal framework. It can learn anything learnable, which is a wonderful statement. So this is how we began to look into this problem. Okay. And so nice thing about conjecture is that at the beginning stage of research is that you don't have to worry about whether it's true or false. And if you answer true or false, you will make progress, right? So this is sort of the beauty of research and exploration, right? We are not judged by somehow make a statement that is false right now, right? So, but if it happened to be true, this, in some sense in our mind, provided a formal justification or at least explanation of Occam reason, right? Because it's aligned with that frame. So we gradually began to settle down in the framework of supervised learning, right? So supervised learning was first proposed by, there's several early versions, and a milestone work is by Leslie Valent in '84. It happened to be his first son was 2 years old. So it could have impact, looking at the child and thinking about the learning framework. And so essentially he used a very beautiful framework to define this IID-based learning, data-driven learning. Right? He said there's a learner which only receive IID sample, but where other sample come from? So he first defined the context. The context is you have a domain, like emails, and you have label space, like whether spam or not. And he's at that time mostly considered binary classification. And then you have a hypothesis class, somehow modeling how each individual's marking the spam. You may use some kind of logical expression or something. And then he introduced two unknowns to guide the learning. One is that there's a distribution, fixed but unknown, like how you draw your email. It's a distribution. You just don't know that distribution, but that distribution is there. It's a mathematical object to talk about. And there's a ground truth labeler that is unknown to the learner. So this is all from learner perspective. Right? The two things unknown, that everything else is public, a priori. So then the learner simply take a samples from data space with a label. This is called supervised data. And then it output, after certain work, for example, a hypothesis in the class that in something better explained. Right? So this is called proper learning. So this is converting somehow statistical observation into an optimization problem to choose models. So this is like H is choosing model. Where the student can be more creative, can just go beyond this given model, and this is usually called improper learning. So those words actually are very important in the talk. And so proper means that you actually return a hypothesis from the class, and improper means you can be creative. I hate the word improper. I really want to call this creative learning. Right? You can creative way to learn, right? And then you will be judged by exams. Namely, you will see a future data from the same distribution that you don't know, and you want to know how close you come to the answer, right? How often you're correct. So this is basically the broad framework. And so since he mentioned this, and actually in practice, people are already doing machine learning, right? Machine learning has been there for even longer time. And at that time, when I was a student at CMU, one of the popular projects in CMU in computer vision is to recognize handwriting and for the post office. And clearly there is not binary classification, it's a 10 digits classification, right? You have 10 tokens. And in modern days, then clearly the token become infinity. Right? Quickly, facial recognition, everyone is a token, right? Every possible being is a token. So this become a learning with infinite labels. Gradually, we are there in the infinite label space. But the framework of Valent continually expand. One just need to introduce a geometry on the label. That's all, right? You introduce a geometry on the label. The label can be very complex. That's still fine, right? So what is learnability? Learnability at very high level means that you see enough data and you can drive an error to zero. Your future prediction to zero from same distribution in the supervised setting. And more broadly, concretely, is that H can be learned with epsilon sample with, for example, M sample, as with M samples. I think later M and N are confused in my slides. I tried to clean up, but somehow M showed up here. And so this gives a more concrete sample and error relationship. And if you can get finite sample into approaching to zero, that's called is learnable. Okay? And there's different notion of framework. I will talk about them later. I will enunciate them in more detail. So supervised learning broadly is basically try to build a good model to predict for future. And it encourages one thing, which we mathematicians always love: do not memorize data and try to generalize. Right? So this is a right principle for mathematical research. And this has broad applications from real application to explaining certain phenomena. So since Valen mentioned this binary classification in '84, even when I was a student, for the binary classification, it was completely characterized. And the only solution they need there is just ERM. So at that time, regularization didn't show up. Basically, they proved that if VC dimension, and if you don't know VC dimension is fine, you can think about your concept space to hyperplane, and your D is just your VC dimension. And VC dimension is just abstraction of that to more broad space. And if that dimension is finite, then it's learnable. And if and only if, right? Give characterization. And in fact, they can characterize the sample complexity in the bound of VC dimension divided by epsilon. So it's linear in VC dimension and 1 over epsilon in the errors.
And with high probabilities with respect to the training data, right?
When the data are drawn from any distribution. So the beauty of Valen's work is he didn't focus on a single distribution. He said in the worst case for any distribution. That is actually one of the key points from his work. So this character if and only if. But for the multiclass, when the label go to infinity, we all know infinity is not a simple concept in mathematics. Many mathematicians appreciate the subtlety of infinity, right? And here too, it takes years for people to try to find notion, just like VC dimension. There's a beautiful breakthrough in 22, and eventually ironed out an extension of VC dimension, and the proof that indeed you can also characterize. And there, they don't have ERM anymore. It went way beyond the simplicity of just optimize. It's used a variety of techniques to achieve that. Okay. So naturally, in this broad setting, not just us, the field also asks, are there simple algorithmic framework template to learn? Right. So for the more general supervised learning, when label become much more complex. And so one of the family of simple framework go beyond ERM is regularization, right? So this can be viewed as a next step framework. And unfortunately, 2 years after Sheldon and I had that conversation on regularization, there's a beautiful work proof that for multi-class learning, namely when label can go to infinity, there are learnable class that cannot be learned by any proper learner. So this result, I think, philosophically is just beautiful for mathematicians, right? If any teacher forces students to write proof in a particular style, you can point to this result. You said student has to be creative to write their own proofs, because sometimes in order to learn, they have to go beyond what you're teaching me as a framework, right? So proper learner is insufficient to learn, and regularization in a traditional way is proper. So this actually said our old conjecture is wishful conjecture. It's clearly it's not correct. Good. Okay. So this leads to the motivation that what is the smallest change to regularization that actually characterize the learning. Anything learnable is learnable this way. So the first attempt we have, so this already after years now, Watson already joined our department. And so we began to have new fresh look of this problem. And essentially, we try to say, can we build so-called localized regularization? Namely, you already know the question you need to answer, then you regularize. Because traditional regularizations, you look at hypothesis, you say, I like this, I don't like this. And the localized means that I need to solve this problem. And then I look at the hypothesis, which one is better for me, right? Because intuitively, we knew that some functions are complex in one region, but could be simple in some other region. So depending on where data are, you can look at the function as complex and simple, right? So this is called localized regularization. And this allows one also to choose so-called piecewise hypothesis to make your hypothesis. And this go beyond proper. Proper means choose one function. If you're linear, you have to choose a linear function. But in mathematics, particularly in numerical analysis, we know finite element is universal, right? You can use piecewise to approximate. Piecewise is improper, right? Because improper against a linear function or any other potential family, right? So this is our conjecture migrate to here now, can we actually universally learn with this type of hypothesis, regularization, namely regularization depend upon not just hypothesis, but also the problem you need to solve. And unfortunately, the 14 result is so strong proof, it's actually extend all the way to here. Okay. So one of the basic challenges basically related with somehow distribution, that is, you may have hypothesis simple in one region, but complex in the other region. But then if you need to solve problem in the junction, it depends upon whether your overall distribution comes from a particular region or the other one. So it's often depend on not just the problem you need to solve, but the distribution of the data you come from. But notice that distribution of data has no labels. It's so-called unlabeled data. So this connects us to think about, can we use unlabeled data to build a regularizer? Is there a way somehow we have unlabeled email, just by looking at your distribution of email, somehow you can build a better regularizer? Right? So that's the other piece of information that for supervised learning, you have before the supervised data occur, right? So essentially, we're able to try to build upon this unlabeled data, try to regularize, and we can update the regularization depend not only on the hypothesis, but also on a bunch of unregularized data and the question you need to solve. And this, we showed that indeed actually is universal to learn. Deterministically, there's a factor of 2 laws. I'm not going to talk about this result. I will be more talk about if you allow learner to be randomized, namely a learner will output a distribution of hypotheses rather than a single hypothesis. So that when you need to solve a problem, you go with your own distribution to draw a hypothesis to solve. So this came much closer to the more classical AI method called Bayesian method, Bayesian-based learning, right? It gives you a distribution of schema. And we show under this schema that even though the original data may contain certain noise, then you can actually characterize learning optimally if you build regularization this way. And it also allows us to explain certain universality of, for example, Bayesian learning. Okay. So for this, let me iron out a simple model for, we're going to do our main analysis, even though it's tend to some other model, but this is a much cleaner model, particularly for giving a talk. It's called transductive learning, introduced by Vapnik, the same V of VC dimension, in the 70s. So, about 10 more years before Valiant's work. And, he's I think, Russian educated mathematician come to US, right? So maybe his childhood learning has something to do with this model. I want you to be the judge. So essentially he said, here is a learning model. The other was to select n data points. This is a worst case analysis. Valiant said there's a worst case distribution. He said there's a worst case collection of data. And then at test time, you will choose one of the random data to test. The rest for teaching. The rest are for the supervising. So then for other data, you give the label, and then you ask a learner to answer this question. Just one question, right? And if answer correctly, you score positively, otherwise in 4, otherwise you score negatively, at 0, okay? If there's geometry, you can talk about how close you are, okay? So since this is in math department, let me convert this abstract model in a language maybe mathematicians can appreciate. So here is my reinterpretation of Vapnik's model, and that is so what is data, right? Because when abstractly we think about data, hypothesis, they all kind of jargons, right? But let me give you some of the more concrete way for me to think about it. So data space is just a collection of problems. Just, for example, problem book, right? In mathematics, we have a lot of good problem books, right? And we often separate problem books and the manual, the solution. So let's think about in the modern AI days, anyone can write solutions. Like even ChatGPT can create a solution. So you have this all kind of solution books, manuals. So that is your hypothesis. So solution are the label, problems are the data. Right? This is just what the mathematicians see, right? When you see a problem, you have to give a solution. Solution is the label. right? So clearly there's many solutions, and quickly you get infinite labels, right? So your data is problem, and data set is a problem book, and solutions are the label, and the hypothesis space just collection of book the solution manuals. Okay, the manual doesn't have to be correct or you like or not. Just anyone can. This collection of books. So then, what is the supervised learning or the teaching, and what is learning? So the supervised, let's call it teacher, and so it has to first decide how many lectures it needs to give in a semester, and that is called sample complexity. Right, the number of lectures to give is sample complexity. Okay, so what is syllabus? The syllabus is that the teacher posts n questions from the book, and give the student all the books that could be possible as manuals, solution. That is the teacher's preparation on the before semester start. It's choose n problem, one for each lecture, and the task problem, and then all the books possible, right? But before the first lecture, the teacher needs to choose which book they want to teach, called H star. Because the teacher never tells student which book they teach. Students have pile of books, but teacher choose one of them, his favorite book. Okay, so that is called the preparation on day one. And he will also, maybe in the classroom, choose a random permutation of n elements. He permuted the problem, lectures. Okay? So then what is lecture? Lecture is the typical teaching, boring style. The teacher just write the teach problem on the board and then write the solution from that book for it and turn around and just leave. Does not answer any questions. I'm sure we saw some of those teachers throughout our life. That's the teacher, right? So it's just write the problem, write a solution, turn around your left, and students just stare at the problem and solutions. Right, so that's called the teach lecture. And they will teach n-1 times. That's sample complexity. So clearly students basically don't care about any of those. Say, what is exam? Right? The teacher basically said, I will choose a random problem to test you. And random problem come from the set. I'm not going to choose a new problem. I'm just choose this problem set. Okay. So then basically the teacher just do this exam time, student needs to solve this problem. It's open book, right? Because you have all the other books there. You just don't know the teacher's book. You have all the lecture notes. Right? So there's an open book exam. That is in the perfect way, right? So this basically is a Vapnik's broad framework. So then you're asking, let's look at learners, students, right? Usually we talk about students. Sometimes we tell students, in order to learn well, you need to do one thing. You need to, prepare learning before going to a lecture. Nobody do that anymore, probably. But we often somehow believe it's a good thing to learn, right? Is that you prepare yourself, right? So what student can prepare here? The student already see all the problems, already see all the books. So students can prepare, called preview, right? So let me define a graph theoretical way to preview. How students prepare themselves to take it, to learn before any lecture is given. So the student can do the following. He read all the book on all the problem and write down the solutions. So for each of the book, you can write down your array of solutions. So this will be the right-hand side of a graph, right? And even more diligent student can even emulate the professor to say, oh, what if this is a question mark? And then what's the lecture? So it even build the consistency of a possible professor lecture with which book. So it's build this thing. So this is a bipartite graph. The possible lecture from teacher in equivalent class and possible book in equivalent only for this field problem. So this is a bipartite graph. And each link corresponding a consistent possible set of lectures consistent with this book. You can see student can do this without a teacher. Right? You just, from the problem and book, they can build this. Okay, so this left-hand side, right-hand side, and convergence. And all the right-hand side has n degrees because it has n possible question marks it's facing as random test. Right? So this is this. So then what is the learner doing? The learner doing is that once they see a lecture, and then it has to decide which book the teacher is teaching. Then in the exam time, it can copy down the solution correctly, right? So if a learner see a unique case, that learner will uniquely learn. This is called the teaching dimension. You uniquely teach the book arise, it's the only book. Or sometimes you have ambiguities, then the learner has to choose. And if you choose a wrong book, you get the wrong answer. Right? So the learner is just guess which book to take the exam. So this is the situation. So essentially, the learner choose a matching from left to right. Every left node will be matched to one of the book. So this is left to right matching. And so if you think about the evil professor in your mind, imagine a diligent student did this all matching. The evil professor clearly will choose a book that will mess up the student most, which means it missed the link of student choosing, the student making mistakes, right? So in some sense, for good students, you said it doesn't matter what the professor is choosing in books, you can only miss epsilon n possible matching. So basically, you want to, in some sense, maximize the minimal matching from the left. So this characterize learning in transductive model is precisely characterize learning in transductive model. So once you see this matching language, and so one quickly see this linear programming representation of this. It's just a linear program. And you can actually write down this linear program of all the possible passing students. Namely, you can consider all the matching from left to right. And then you can think about distribution among all the matching. And you set up a condition that all the matching has to be good. That is, the student somehow significant pass. Namely, suppose you have benchmark of optimal learning rate, epsilon star. And if this program is feasible, then it's learnable, if and only if. Because this program characterizes the epsilon errors in learning. So this is why this graph theoretical characterization somehow uniquely defines the learnability. And in our paper, we began to consider a max entropy style of program. So we maximize the entropy among all the passing students. There's different type of passing students, we just maximize them. And this program turned out to be a very good program in the following sense, that it enjoys strong duality in LP. In some sense, its optimal solution is unique, right? And more than that, if you look at the dual of this program, for every book, you have a constraint. So in the dual, for every book, you got a number in solution. And we are able to prove that in the optimal solution, the dual solution against every book is non-negative. So that's one of the important property of this program, that if you maximize the entropy, the solution is non-negative against book. And we will see an array of non-negative numbers. If you're a statistician or machine learner, immediately see that's a distribution, right? Because you can normalize them into distribution, right? So in some sense, when you solve this program, you got the distribution over the book. So in some sense, the student did the right thing, right? Preview is just to look at the problem, to look at the book, and we'll guess which book professor may teach, right? So that's traditionally how you examine. Right? So this essentially, this program just emulates such a student. Okay. So this gave a basic perspective of learning. That is, after you solve this program, if you take a dual variable and you normalize into distribution, you get a distribution over the right-hand side. Yeah, I think I should be rho, but somehow when reformatted, it become R. And and this optimum also produce a product distribution on the right-hand side. And so the Bayesian perspective is following. It divides learning into field phase. At the beginning, unlabeled data are the problems that the teacher gave on day one, right? The student can build a prior over hypothesis after the preview. And then once the teacher began to lecture for the whole semester, the student get more data and it can do base update. Because certain books are gone, it's inconsistent, are gone. So you can do a Bayesian update in the row prime. And then at exam time, you just sample according to your row prime, then you answer the question. You draw the book there. So this is a classical Bayesian learner framework, right? You take unsupervised data to build a distribution of hypothesis. Then you take a supervised data to refine the distribution hypothesis. And when you need to solve problems, you take that distribution to solve your problem, right? So essentially, our proof so far proves that the Bayesian framework is universal for supervised learning. Any problem that is learnable, there exists a Bayesian framework to learn. And the most important thing is to choose a prior, and this program offers you a correct way to choose prior. Then afterward, you do the update. And when we tie with our framework of regularization, we're able to show that basically the movement from row to row prime follow a regularization locally using the unsupervised data. So that's basically allow us to prove the unsupervised data plus the question can build effective regularizer that is universal for learning because it provides implementation of this complete Bayesian framework. Okay, and in some sense, it goes along the KL divergence, just like in calculus, right? The only one concept I remember now as a non-mathematician, the Taylor expansion. The first term is, FA equal to F0 plus the derivative times A, right? And that is, in some sense, a notion of a divergence between 0 and that, and the 0 is our prior, and that is posterior. So in some sense, it goes with this linear decomposition. And that term came out to be the local regularization. So this proves this local regularization is universal for learning. And it's also highlighted the maximum entropy somehow is important because currently if we change objective function, we haven't been able to systematically argue whether it's good objective function. I think it's a beautiful question mathematically. So this gives us a kind of beginning of understanding, at least from this single word, it's a long journey, and we feel like we took some basic step, not just try to understand regularization, but also begin to gain new insight into Bayesian learner, and also particularly about unsupervised data. Because unsupervised data is important element for learning. At least we showed, instead of just doing regular clustering, there's another way to use unregularized data from perspective that is build a good prior using unregularized data. And so this allows us to connect with more broad learning framework, such as the Bayesian and maximum entropy. And it did also lead us to some new questions along the way. We were able to prove the following compactness result for learnability, right? So once the label space data and hypothesis become infinity or uncountable, then one of the fundamental mathematical questions is learnability compact, right? So what is compact? This means that if you have counter example, you must have a finite counter example. Or if it's true for all your finite projection, whether it's still true for you, right? So for example, a classical theorem in graph theory for compactness is a coloring. Imagine you have infinite graph, right? Graph has infinite nodes. And you're asking, is this graph 5 colorable or 4 colorable or 3 colorable? The following is true. If every finite subgraph of this graph is 3 colorable, then the entire graph is 3 colorable. So it has this compactness. So we were able to prove using this machine learning to show that if every finite projection of this uncountable setting of learnability is true, then the entire uncountable space is learnable in the same language. And it leads us to many other questions about how much sample we need, in which way we deal with unsupervised data. So to a larger degree, it leads us to look at the role of many other data rather than supervised data. So particularly, we want to understand more about how unlabeled data are useful for learning. So this is still ongoing project that we are still pursuing. And it also leads us to something else, going beyond the supervised data. And it gives us broad perspective and to look at some other learning phenomena like transfer of learning, right? So there's many styles of transfer of learning, multiclass, lifelong, distillation, self-learning, right? So, and many of those can, in some degree, characterized by regularization, right? So there could be much deeper angle to look at them. And the other one related with unsupervised data and its extension is chain of thought, right? In modern days now, we see chain of thought somehow improve larger language model. And so there's one recent elegant result, which I really like, that I've been talking with Atu on this, that is you can define two learning class. One is called end-to-end learning class that you allow you to apply chain of thought, but you don't give the student learner chain of thought. And the other ones you give a student chain of thought, supporting all T steps. So then for the binary case, if your function is keep on appending one token, this token just 0, 1. Right? So you can see you generate binary sequence. And in that case, this work from TTIC essentially show that without chain of thought data, you need much more sample to learn. But with chain of thought data, you can improve the sample complexity exponentially based upon how many steps you do the chain of thought. You're missing more and more, right? So this type of data actually highlighted a different type of the unsupervised data is something called auxiliary data, right? Because you always want to solve a last problem. So everything happening in the middle is auxiliary. So the question is how auxiliary data, just like unsupervised data, help one to learn, right? And so in this broad context, and it's connected with my current project with math department with Zhixiang and Xiaohui, that is there's other way to arise auxiliary data showed up. For example, there's a variety of possible beautiful learning problem from physics that you have a PDEs, model of physical dynamics, and then you have observation of your data, and you want to somehow learn its dynamics, right? Either in a forward manner to approximate the final result, or in the inverse manner, like solving inverse problem. Or you may try to build like operators to allow you to assist the future faster learning in this broad framework. And I'm not going to go too much detail. I'm sure in the next short months, Zhixiang will work on his thesis. He will talk more on this thing. And so one of the central questions is basically, can we efficiently obtain those auxiliary data to improve our learning, particularly against non-smooth functions, right? Usually people assume function are smooth, then it's almost like have limited VC dimension and so on, right? So it's related with this type of language, certain finiteness. And but for non-smooth smooth function, it's somehow correlated, somehow you go to infinity. Things can go infinitely bad, right? So in which way some additional information and data and knowledge can help this learning. And so currently, we're largely just focused upon simple model right now. It's just the time-dependent heat model, right? And hopefully, eventually can be extended to other model. As it's extended more, I know much less because my math training gradually hit this boundary. And luckily, we have wonderful mathematicians working with us and in the room. So essentially, in this particular setting, we are able to think about auxiliary data as following. that you have a label, you try to learn this function, and this function U is the primary function in the PDE, but this boundary function, false function, is also defined on time and space. It can be considered as auxiliary data, right? Because you don't have to give that, you can still learning in this supervised learning. But suppose you have that data, how do you use it? And Zhixiang and Xiao were able to show that if you use it to build some kind of energy-based regularization, so somehow this energy-based regularization, almost like the regularization for the chain of thought, right? But you have certain mathematical model somehow underlying the physical PDE, and that somehow can be built into a regularized term that allow you to incorporate the relationship between auxiliary data and the supervised data. And so Zhixiang is able to show that upon the optimal trade-off, you can improve the performance when you don't consider the sort of physical inspired model. Okay, so this, I think, probably provides some other more concrete angle to say regularization may not just exist abstractly, like what I'm talking about is Russian teaching and the students, but once you have a physical model, there could be much more natural way to think about regularization. And so with this, basically, it tied with some of my recent thinking about learning theory, that hopefully try to understand the role of unlabeled data, auxiliary data, and in some sense try to understand what are the right way to transfer knowledge or learning experience and so on. And are there sort of more unified framework to somehow capture them? Thank you.
So, questions, comments from the experts and the unexperts?
When you were showing the list of PDE inspired, you said you just focused on the heat equation because it's sort of more approachable, but you were also talking quantum mechanics, or is it just in principle, if you have a physics guided system, you could try to do this kind of learning? Or
I think as a first step, clearly the heat equation, given I think both its PDE are relatively somehow simple and nicer, and also given they have much more broader theory numerically also about this family, and there's also much more early body of the literature. So in some sense, we are hoping that some of the observations there gradually can generalize, right? And just like when we started with regularization, we try to start as simple as we can. And here, I think also from Zhixiang and Xiaohui's perspective, is that it's good to pave the way from a simpler PDE. Then gradually you can see as PDE evolve, what are the different phenomena showed up, and the simpler one also, I think, allow us to maybe consider questions about what type of regularization is necessary and essential, for example, to achieve a certain degree of convergence and precision and so on, right?
And in your simpler PDs, are you using physical data that is inspiring those PDs? Can that help you? The huge mountains of physical data connected with heat equation.
Right. There's also, there's many, the physical generating model and so on. I think the hope is that gradually we can tie more with this body. But the hope clearly continues is try to expand, right? To see what are the intrinsic essence that can characterize the boundary of which family of the learning approach. I think as PDE become more complex, I'm sure the language probably has to be refined. Right. But unfortunately, my own training, in the past, in the 90s, one of my research projects is on mesh generation. But unfortunately, at those days, I couldn't quite understand too much about Hilbert space and so on, even though I was sitting next door to Gil Strand. I was reading Strand the fix at that time to try to so I did manage to, with my colleagues, to solve a major open question in three-dimensional mesh generation. But my own training of numerical PDE was subpar. Luckily, they are more expert. But at least I began to appreciate that period of interdisciplinary days when I was working on mesh generation, couldn't fully understand why for flow you need this type of element and so on. And luckily, those days, Gil Strang is a very nice man at MIT. And he just said, you can just come to my office anytime and I can answer questions. So eventually, not only he teaching me every time I go there, he actually has finally, like maybe 5 copies of the Strand fix. And when I was leaving MIT, he actually took one of the book and he said, because I'm always use a library book. Then he said, Shanghua, this copy is for you. You care so much, this book is for you. So I still have that book in my office. Yeah, I maybe should go back to read much more.
One of your learning books.
That's one of the, it could be auxiliary data. It could be auxiliary data, yeah, for learning, yeah.
So questions or comments, or maybe from your collaborators who'd like to
you talk a little bit about expand. Yeah, I just want to expand maybe a little adds on the why the heat equation, as opposed to more general, PDEs and
start simple.
So yeah, start simple is one reason, but we're trying to look for the generic property of the regularizers. So in this case, we have this kind of so people already done some kind of static case where there's exact regularizers that you can derive this kind of properties. But in terms of the dynamical system, it seems that the regularizer they study is very degenerate. So this one is kind of balancing between this data loss in term, the unlabeled data and the physics part. So you can try to find the sweet spot that you can do some kind of optimal, stuff there. So. Yeah, so that's this thing. But I have a question about what if you have distribution shift? These are learnable in some sense,
I think, yeah, distribution shifts are broadly in the framework of transformer learning. And so I myself don't have a sort of the satisfactory explanation of, but that's among some of the area periodically I go back to think whether there's much sort of common language to connect this way. Yeah, but you can consider, for example, if you have something built up, data for the prior distribution, and when new distribution occur, then there could be certain, I think, more systematic manner to. But fundamentally, you have to understand the geometry of your label space, right? Because whatever transfer eventually need to look into the geometry of your label space. Yeah.
So could I ask a question?
Sure.
Thanks. So it seems like a lot of the talk focuses on sample complexity. I wonder if you could say a little bit about time complexity.
Right. So currently, given this math department, then I feel that, no, I'm just joking. So we are dying to see some algorithmic result. The current whole construction is a proof of concept. It's only proof certain style of learner exists. But currently, we don't have any concrete result yet to say that this will lead sort of efficient learner of certain style. That's a wonderful question. Yeah. So it's very high on our list, but we have been working for a while. We don't have any concrete thing yet to say. Yeah.
Okay, thank you.
Are there any other questions from people on Zoom? So, questions or comments? See, is your other collaborator in the room too?
Yes. I have a question.
Okay.
So for this student-teacher model, when you talk about generalization error, so are you taking expectation over the Bayesian is for the Bayesian risk, or?
So in that particular model, basically, you're taking expectation on a random problem become a test problem. Right. So in some sense, that is almost an emulated language of similar to valence. Say you have arbitrary distribution. It's just that here is a bunch of problem. One of the problem uniformly will become your test problem.
Yeah, but my question is, you output a distribution of the hypothesis.
Right,
That's
right.
also random. So you take expectation.
Right. So then basically you measured by the probability that you are
So
correct.
it's random over the
Right.
and also over
Right. So the main part is a random over testing problem. But as students, you were judged by your expected performance when you are using your randomized learning. Right. That is correct. It's just like all the Bayesian learner is judged that way. Yeah. Do you want to say a few words?
Sure.
Please do.
I guess I work with Shanghua on learning with auxiliary data. And I guess the toy example that we were considering so far was the chain of thought framework. And I guess we also were considering the transductive model. Yeah, I guess what we have shown so far is if you allow for arbitrarily large label sets, then you even small even when you're learning some final token of some short chain of thought, you in general, this is not like a learnable problem, but if you're given access to the chain of thought, then you can do pretty well.
Well, thank everybody, and particularly Xiaowei very much. And Shanghua, congratulations.